Students, I think, would benefit from choosing SWOCC because it gives them an opportunity to get involved at a more hands-on level earlier in their career. Students choosing to come to SWOCC benefit from having opportunities at the freshman and sophomore level to get involved in research that can carry them forward in their career while still maintaining the same academic rigor as they would experience at a four-year institution. The day in the classroom in physics and engineering starts out as sort of a conversational approach to the material that we're looking at, whether it be solving rocket science problems, whether it be designing bridges, whether it be designing electrical circuit systems. It's usually a conversational approach that leads to a lot of questions. I always tell students if they're doing science well, they'll always leave science class with more questions than they got answers to begin with. And that's to drive the intellectual curiosity of the students. And that's what I try to do, making things interactive as possible and letting them foster that curiosity and develop those critical thinking and teamwork skills that they need to succeed as they go forward. You're dealing with a class in physics that's typically between 10 and 20 students. That gives you plenty of time to interact, ask questions. You get more direct responses from the instructor. And SWOCC being a small enough school, there are instructors that you will see a number of times, so you get to develop sort of a rapport with your instructors and truly do become more like mentors than they do become teachers. The biggest thing it brings is a sense of opportunity. It gives us a chance to revisit how our curriculum works. It gives us a chance to incorporate new ideas, new equipment, and it also provides the students with ample opportunity for new projects and new developments in terms of research. The physics and engineering programs at Southwestern are a great way to begin your journey in a professional STEM career. And welcome everyone to our debut of the Physics and Astronomy lecture series for the 2021-22 academic year. I'm Dr. Inouye. I'm the professor of physics here at Southwestern. I'm also the head of the engineering department. I'm happy to have everyone joining us today. And happy to share some news with our department and our students and some important program information that's actually coming up soon. Just to let you have an idea of what's going on here at the department. Coming up in the coming weeks, we will be announcing, we're currently finding a home for our annual art exhibit that we do, showcasing student art related to STEM courses and otherwise, in this case, tying into what we're calling the Strategic Initiatives Project, which ties into sort of military involvement and political involvement in advances in scientific technology. So we'll be housing that, and there'll be more information on that to come. As far as student projects, we are happy to be back in person this term, and we will be building on some of our projects with our SPEAR project, which includes our space physics and experimental atmospheric research. We'll be doing more of our balloon launches. We'll also be continuing our local micrometeorite searches and continuing our search along with the International Astronomical Search Collaboration to continue to search for unidentified near-Earth asteroids. If you're a student that is interested in participating in these projects, you can reach out to myself, Dr. Coiner, at aaron.coiner@socc.edu, or you can reach out to our department collaborator and researcher Crystal Hopper at physics-engineering@socc.edu. Both of us will be glad to help get you involved in our SPEAR projects. And also, as I said, thank you for coming to our lecture series. And if this is something you like to see continue, we recommend you contact if you would like to potentially donate to help facilitate further lectures. you can always reach out to the SWOCC Foundation, let them know that you're making a donation on behalf of the Physics and Astronomy Lecture Series, and we'll use that funding to help bring more guests like our guest this month. I am proud after kind of an extended time loop trying to get everything to work out. Proud to invite a friend and colleague of mine, Dr. Holly Gilbert. She's currently the director of the National Center for Atmospheric Research's High Altitude Observatory in Colorado. Before that, she was heavily involved in the heliophysics science division at NASA Goddard, and prior to that, spent a few years as a research scientist at Rice University. I worked with Holly at both Rice and at Goddard, and I'm proud to call her a friend, a mentor, and an outstanding scientist and a colleague. So I hope you guys will be able to learn for things, and I hope you guys will be able to learn a lot from her talk, and I know you will. And with that, I will turn it over to Dr. Holly Gilbert.
Thanks, Aaron, so much for inviting me to be here and the introduction. And I want to thank everybody for spending part of your evening with me. I'm really excited to be here. And I'll just go ahead and dive in to the talk, which I titled A New Era of Solar Observations. There are many different types of observations that I could talk about. We have missions that have gone up recently over the last few years. We have ground observatories that have just been opening, and it's a fantastic time to be in solar physics. I'm going to focus on a couple of probably not as well-known observatories, one being space-based and one being on the ground. And I've been involved with both of those, so that's why I'm focusing on that. But again, there are a lot of exciting new observations in solar physics and heliophysics in general. Eclipses are historically probably one of the earliest forms of observing the sun, and actually the only way back then to observe the solar corona, which is the extended atmosphere of the sun. We still use eclipses to study the solar corona, but we also have fake eclipses that we call coronagraphs, and I'll talk about those in a bit. But moving on a little bit, so let's just talk about in 1946. This is an amazing image of a solar prominence, which is a very large structure, magnetic structure with hot plasma. The plasma is not actually as hot as the solar corona's plasma, but you can see this, what we think is like a helical structure. And the edge you're seeing there is the edge of the surface of the sun. So you can see how large this thing is, and it is erupting from the sun. This is taken in the line of H alpha, which is at 656 nanometers. We've known for decades now that the sun, some of the fundamental things about the sun that we need to understand are plasma, magnetic fields, and that magnetism really is central to our understanding of many physical processes. Also, magnetism spans both time and space. Next slide, please. So moving on to a couple of decades later, Skylab was the first sort of international, or space station, not international, but it was the first space station. And we were able to discover coronal mass ejections, these major eruptions coming away from the sun because of Skylab. We didn't really know that they existed in the corona before this mission. The corona, of course, is extremely diffuse. And so this is the fake eclipse that I was talking about. You block out the very, very bright disk of the sun so that you can see the very diffuse corona and those streamers that are extending outward from there. White light is what is producing that image that you see of the corona, and it's really from Thomson scattering, so scattering of light off free electrons. And so again, we can't observe the corona, and especially the extended corona, unless we block that very bright disk. Next slide. go into the 1990s, and all of a sudden we're able to observe the corona on the disk in ways that we weren't able to do before. And this is because this is a space-based mission of SOHO. This is actually data from a later mission, but it's demonstrating that there are many layers, temperatures that comprise the atmosphere of the sun. And we are seeing a composite image here of at least, I think, 3 different temperatures, very, very hot. So the corona is extremely hot. It's much, much hotter than the surface of the sun. Now, why do we even want to study the sun? I mean, first of all, it's intrinsically interesting, but we do care about it, especially now that we depend on technology because of space weather. So the sun drives space weather events, and sometimes they impact us here on the Earth. So in order to understand what triggers those solar eruptions, those coronal mass ejections, and those erupting solar prominences that I just talked about, we really need to understand the magnetized corona. The magnetism is what drives those eruptions. So I basically consider the corona like the breeding ground of space weather. And in order to understand the link or the system between the sun and the Earth, it's really a chain. You have to understand the magnetic fields in the corona. Next. One of the mysteries that has remained that we still struggle with today about the corona is why it's so hot. It's a million plus, up to 10 million Kelvin. And the surface is on the order of 6,000 Kelvin. So there's a significant increase in a very short distance in temperature, and we don't really understand exactly why that is. We call this the coronal heating problem. And so in understanding more about the corona, the magnetic fields, different waves that are happening in the atmosphere, these are the types of things that we're studying and have been studying for a long time to understand these types of mysteries. And in fact, this is one of the reasons I got into solar physics, is because we still have so much to learn about the sun, even though it's essentially in our backyard in terms of astronomy. So it's really exciting that we still don't know everything about the sun, but we're making a lot of progress, and partly because of some of the new observations that are coming online that I'll be talking about. Next slide. As I mentioned, the origin of space weather really has to do with those magnetic fields on the sun. And these fields, you can't really see them. The hot plasma outlines them, so you can really see those loop-like structures in the corona as you're seeing here. But these fields leave an imprint on the intensity and the polarization of the light that it's emitting. Observations of the polarized light, they're very complicated, and they really need to be interpreted in terms of the magnetic field. And that interpretation relies on complex polarized radiative transfer community models. So this is not a simple problem to address. Next. So in order to study the origins of space weather, we really are taking a two-pronged approach in the community. On the one hand, we need to understand the very small scale magnetic processes that are driving these very dynamic phenomena. But on the other hand, we need large scale synoptic observations to understand, again, the system as a whole, the sun as a system, and the system of the sun and the Earth. And that will then enable better space weather forecasting, which we are still in the somewhat early stages of being able to do for space weather. Next slide, please. So Mauna Loa is an observatory that's run by the High Altitude Observatory, HAO, where I work. And it's located on the Big Island of Hawaii. And in fact, it has a beautiful view of Mauna Kea, which is where a lot of other observatories are located. But again, I want to emphasize again, the sun's magnetism operates at all spatial scales, both small and large. And the research that's aimed at understanding the solar atmosphere is in fact a core strength of HAO. And the instruments on the Mauna Loa Solar Observatory are designed to carry out the synoptic, the large scale observations of the solar magnetic activity. We've operated coronagraphs, the fake eclipses, so that we can view the outer atmosphere since 1957. And to this day, we are still taking unique observations of the solar eruptions as they occur. And that is because you'll see in the next slide, please. These are our observers at Mauna Loa. We have 3 full-time observers, and as you can see, they're wearing masks because they were able to continue working through COVID. They were only able to have one person in the building at one time, but Lisa's standing in front of the monitors that show the current observations of the sun's corona, as well as the sky conditions and also the hardware status. And the instruments, they're accessible through a flight of stairs that leads to the upper floor of the dome. And then the tower that you can see with Ben is next to the tower that you're seeing in the other picture. This is actually a NOAA tower, and it's used to collect atmospheric measurements. And they've been using that since 1950s. And those measurements actually, although that's not related to our solar measurements, they've shown a rise in carbon dioxide concentrations in the atmosphere. So we share that space with NOAA. And next, please. We offer a calendar of data. So you can go to the Mauna Loa website, and we have, not only do we have corona data, white light coronagraph data, we have other data as well, and I'll mention some of that. But you can go on and you can click on certain days, whatever days you may be looking for, and look at what data is available. So this is a very easy, accessible way of grabbing data if you're interested and if you're doing solar physics research. So I encourage you to go there if you're interested. Next, please. I mentioned the coronagraph that we have, and as you can see, the movies here. So the blue one is the K coronagraph, and this is the world's only ground-based white light coronagraph. This is capable of observing the source regions of those mass ejections because we have such a low field of view. So you can see the black outline of the coronagraph of the disk that blocks the bright disk of the sun. And if you can see, there's it's a dotted line, and that's actually the surface. So we're observing almost all the way down to the surface. And this is very difficult with this type of instrument. But this is allowing us to see the region that's critically important for where these eruptions originate. And they accelerate in this region as well. So our coronagraph data is providing a gap in observation. Some space-based coronagraphs provide observations higher up, but this is really an important region of the sun. We provide data in multiple wavelengths, so not just the white light, as I mentioned. So we cover the chromosphere and the corona. We provide real-time activity alerts and solar activity logs through our website. We also even have activity logs, not just from Mauna Loa, but even some space missions that were led by NCAR dating back to 1973. Like I mentioned, Skylab was one of those. We also provide analysis tools, software packages, data processing and calibration software to the community. So we're very community service oriented. We also work with the community on special observing campaigns and data requests. And of course, all this data can be freely accessed from our webpage again. Now, I want to sort of focus a little bit on the Doppler velocity image that you're seeing there. This is from spectropolarimetry, and this is a core capability at HAO, the High Altitude Observatory. And it basically involves inferring the plasma and magnetic properties through the measurement and understanding of polarized radiation. Here you can see this Doppler velocity map. And the polarized spectrum of the sun, and it encodes a wealth of information on both the thermodynamic and the magnetic properties of the atmosphere. There's a huge challenge, though, in unveiling the information that it contains. Scientists have to perform very sensitive spectropolarimetric observations and then carefully reduce, analyze, and interpret that data. So it's not an easy thing to do. And next slide, please. We actually host a school to teach people how to do this. I must have asked, is there one more before this? That's okay, if not. So we do have sorry, I'm missing one, that's okay. We actually host a spectropolarimetry school. We weren't able to host it this past year because of COVID, and it really is a hands-on type of school. If you're interested in learning more about it, let me know and I can point you in the right direction. So sorry about that missing slide there. Okay, going back to coronagraphs. So again, the region that the Mauna Loa observations fill is an important gap, and it really augments and helps the space-based coronal observations. So you can see on the left that this data was provided by NASA on the outer part in the red, and the K-core coronagraph from Mauna Loa in the blue. So the data, they were coupled with a model to show that the region from the source of that coronal mass ejection was actually magnetically connected to the Earth. And if you look on the right and you see that little circle where the arrow is pointing, that's where this originated. And not only that, but this was a location of gamma rays that were identified in the K coronagraph data. And you see the long extended sheet. That's an actual current sheet. And that's how they know that was connected to the Earth. So this is really important, again, to combine data and making those connections. So Stereo A is a NASA mission, as is the NASA LASGO. So putting these all together allows us to see that extended atmosphere. And we have so many different types of observations. It's really critical to combine them and use as many of them as you can at the same time to make those connections. Again, it's an extended system. We are actually now incorporating, we have coronal mass ejection alerts that are almost real time. And we're incorporating those into NASA's Community Coordinated Modeling Center. They have scoreboards, so they keep track of coronal mass ejection alerts, solar energetic particle alerts. And in fact, NASA's Johnson Space Center, they have a space radiation group, and they're interested in this data as well, because astronauts, of course, are susceptible to space weather. And so by providing better forecasting through this type of data, and in addition to other data, but this is really useful for that type of forecasting. Hopefully, eventually, we'll be able to predict when these things will occur and when they're going to be geo-effective, meaning they impact the Earth. But again, it's a matter of combining the correct data. Next, please. So observing coronal magnetic fields is rare. Again, you can see the plasma outlining them, but actually observing them, getting the magnetic field strength and other properties of the magnetic field is very difficult. One of the instruments located on Mauna Loa is the coronal multi-channel polarimeter, or COMP. And this was used in a science article by an international team. And what they did is they mapped the global magnetic field of the solar corona. And you can see those maps in the left, those two maps. This was really unprecedented. They used the COMP linear polarization and the Doppler data, and they derived density from the iron 13 line ratios to determine the coronal magnetic fields in the corona. Now, as I mentioned, it was unprecedented, but this represents a two-dimensional map. This is great, but ultimately we really need a three-dimensional map of the magnetized solar atmosphere, again, if we're really going to make progress on space weather prediction. The other image on the right, that was the K-core, and although you can't see the coronal mass ejection in this particular one image, this was a community-led paper in the Journal of Space Weather, and this shows the early stages of a coronal mass ejection. So again, using COMP and the K corona is the K coronagraph data is really useful. We call this sort of helioseismology or magnetoseismology applied into these observations. Click, please. I think you have to click twice on next two clicks. I think I had this problem with my own. It's stalled. There we go. Oh, that's fine. The other image that just popped up, sorry about that, Dallas, is an upgraded COMP instrument. And in this, that's on the spar at Mauna Loa. And the longer instrument there is the upgraded COMP instrument. And the one that's next to it shorter is the K coronagraph. So just to show you that we are actually making upgrades, and this is leading to another improved observatory that I'm going to be talking about next. So what's wonderful about the upgraded comp are a few things. So if you remember those two-dimensional maps that I showed, the field of view is not very large. I mean, it goes out just a little bit beyond the solar surface. So we're going to increase what we have. This has actually been done. Increase the field of view, increase spatial resolution, and also the wavelength coverage. So you can see this that spans all of these different, I think there are 9 different wavelengths. And then you can see their temperatures, the relevant temperatures, the line width, and the spectral resolution. So this is a pretty neat improvement. And this is an instrument that's really a pathfinder for Cosmo, which is going to be the improvement or the next observatory that we're transforming Mauna Loa into. And so I'll talk about that in just a second. But next, please. Just to show you some hot off the press data. This was just from a week or 2 ago. In the next slide. Now, this is very dark, so I apologize, but it's very exciting. We have a few of the lines, 1074, 1079, and this is all nanometers, and 789. They look really good. You can see that bright corona. And this isn't even completely done yet. We're still in the commissioning phase, meaning we're not taking science data yet. They're still tweaking the instrument and the data to make sure that we're getting scientific data. But we also have chromospheric lines. If you can look in the very top left corner and then on the top right corner, those are chromospheric lines, and you can see the bright dots along the edge. Those are solar prominences sticking above the disk of the coronagraph. And in the bottom right, it just shows the difference between the comp field of view, which is the blue, the light blue, and the UComp field of view, which actually extends quite a bit. And so that's very useful. We're very excited about these new observations. In a couple months, we'll actually be obtaining science data. Next, please. So this brings us to Cosmo. NCAR, HAO, and the university partners that we have, so they've formulated this path forward, and that is to transition Mauna Loa into Cosmo, the Coronal Solar Magnetism Observatory. And this is really going to allow fundamental research that drives a better understanding of the predictability of the Sun-Earth system, as I've been talking about. And it has 3 main components. First is the white light coronagraph, the K-core, which we've already seen the data for. And so that's exciting. That's already been operating at Mauna Loa. There's a second component called ChroMag, and that's actually a chromospheric magnetometer. And so that's going to give us synoptic data of the chromosphere in different lines. And it's a very versatile instrument. So we're very excited about that. That is not deployed yet at Mauna Loa. It's actually sitting on the spar here in Boulder at our MESA lab. And this is because of COVID. It severely delayed the deployment of ChroMag. So hopefully that will be online early next year. And then thirdly, the large coronagraph. And if you see the picture at the top left, if you can see there's a person, that's an artist interpretation of what the Cosmo Observatory is going to look like. So as you can see, the person is pretty large. And this coronagraph is going to be 1.5 meter diameter, and it will be able to gather light to obtain measurements of the very elusive line of sight component of the magnetic field in the corona. And this is, again, this is the missing piece to obtaining the 3-dimensional magnetic topology. We are in the first phase of this project. We are looking at different sites because it's really important. If you see the image with the thumbs, we need very dark coronal skies. And dark is different. This is a different meaning than the nighttime observers. But you can see just the difference between sea level and 10,000 feet. If we wouldn't be able to observe the corona at sea level in this image. So it's very important to pick a good site. Mauna Loa is one of those great sites that we possibly might be able to build on, but NOAA owns the land, so there's some we'd have to negotiate. Anyway, so that's one of the things, and then really reducing the risk of the large coronagraph design, because this is a pretty large telescope. It's complicated. I think really the advent of these larger aperture telescopes, and this all includes the DKIST. I'll talk about that in a second, but DKIST is probably one that you've heard about. This is the new large telescope in Hawaii on the island of Maui. But Cosmo and DKIST, those types of large aperture telescopes, I think these are really going to open a new window on our understanding of coronal magnetic fields. You can see the theme here of the coronal magnetic fields. I think I've said it a lot. So I think we can move on. Next, please. Now, oh, there's that slide that was missing. I already talked about that school, so you can move forward. Sorry about that. I don't know how my slides got confused. And if you want to hit, this is an animation if you want to play the movie. And this is an instrument that is in DKIST. So again, this is the large telescope that's just now about to start being online with scientific data. And this is the Daniel K. Inouye Solar Telescope, which is DKIST. And so the start of the operations has been delayed due to COVID, but this is the largest solar telescope by far in the history of the world, really. It will provide the highest spatial resolution observations of the sun that have ever been attained. And this is what they're going to do, is they're going to zoom into the small scale processes taking place in the solar atmosphere. And so that's important. As I mentioned, we have this sort of two-pronged approach, and this is the small scale important observations. Now, one of our instruments that was built at HAO is actually what you're seeing, and this is the visible spectropolarimeter. And it's a novel wavelength versatile spectropolarimeter that can measure up to 3 spectral windows simultaneously. And this is anywhere in the visible part of the spectrum. And so this is going to enable multi-line spectropolarimetry and really, again, will allow us to perform magnetic and thermodynamic tomography of the sun's atmosphere. Okay, next, please. Let's move into space. So those are the ground-based observations that are exciting. And again, DKIST can be an entire talk in its own, and maybe you've already heard about it, but it's an amazing, amazing observatory. And again, Cosmo, we're excited to have that synergy between those two ground-based observatories. But again, I'm moving to space now to a mission called Solar Orbiter. Now, this is a ESA-NASA collaboration. ESA is the European Space Agency, and they've had very productive collaborations in the past. And SOHO is really, it was groundbreaking. It allowed us to see images of the sun from space that we had never been able to see before. And so that was really an amazing mission. There's still, some of the data is still being taken. And then Ulysses was another groundbreaking mission. So Solar Orbiter is another what I consider amazing mission. And I was involved when I was at NASA as the project scientist on the NASA side. And I want to actually, speaking of project science, I want to make sure that I give credit to Daniel Mueller from ESA, because he really provided a lot of these slides, as did the teams of all the instruments. Now there are 10 instruments. This is a very large suite of instrumentation. They're both remote sensing and in situ instruments. And so we're able to use this mission to study all the way from the surface into the solar wind. So next slide. Luckily, it launched February 10th of 2020, right before really things started shutting down for COVID. And this was really lucky for us because this is truly an international collaboration. We had so many international visitors at the Cape in Florida for the launch. And as far as I know, there was no big COVID outbreak. So I feel like we were very lucky. Otherwise, who knows how long this would have been delayed. So that was a really neat experience. Next, please. Excuse me. Now, the overarching goal of Solar Orbiter is really understanding how the sun creates the heliosphere and how it controls the heliosphere. It's a living entity. And then also, what is the variability and how does that change with time? So these are very important goals. And again, the combination of the observations, the in situ and the remote sensing combination is very powerful. So this is and it already is providing high resolution imaging and spectroscopy of the sun, both with detailed in situ measurements, sort of sampling of the plasma of that surrounding heliosphere. And this is a mission about linkage. It's really going to link the observed solar wind streams, their source regions at the sun, linking what's happening on the surface with beyond, how that's connecting and linking to the spacecraft and beyond. And one of the things that's going to be really useful and has already, we're already in the planning stages with, I'm going to talk about in a second, is the synergy between another mission. But let's go to the next slide, please. Now, this has been in what we call a cruise phase, and that means it's not taking the nominal like science data yet. Oh, I'm sorry, I already talked about it. Next slide, please. It's hard when I'm not controlling my slides. Perfect, okay. So this is a mission summary, but we've been in the cruise phase since launch, and we'll start operating in the nominal science phase in November of this year. And that's when there's going to be an Earth gravity assist maneuver. Now, why are we even using these gravity assists? And this is because there's a very, very cool aspect of this. And you can click the next one, please. There are a couple of unique things about Solar Orbiter. One is the fact that there are 10 remote sensing and in situ instruments together, a very nice payload. But also the orbit. And so it's going to use gravity assists of both Venus and Earth to kick the orbit of the mission of the spacecraft out of the ecliptic. And so it's going to be getting out further and further as it uses Venus and Earth to change the orbit. So it turns into a very elliptical, very high orbit. It's also getting fairly close to the sun within Mercury's orbit. So again, these are some of the very unique things about the mission. During the nominal mission, after this Earth gravity assist, the remote sensing instruments are going to start their nominal science operations. Now, up to now, through the cruise phase, the in situ instruments have been on and taking data. But the remote sensing, which is basically imaging of the sun in different wavelengths, and I'll talk about that, that's going to start in these 3 windows of 10 days each. So of course we want one at the perihelion for each orbit, because that's going to be interesting getting data that close and imaging the sun that close, but also the ones that are at the higher latitude because of the kicking out of the ecliptic. And so, you know, combining these, again, they're looking at ways of making sure that there's collaboration in the joint in situ and remote sensing operations. And then next slide. The other thing that they're making sure they're doing is collaborating with another mission, which you've hopefully have heard of, Parker Solar Probe, which is another amazing mission. This launched in 2018, and this is going very close to the sun, within 9.5 solar radii. So it's extremely close to the sun. It's like if you consider a football field where the sun is on one field post and the Earth is on the other, Parker is going to be on like the 4-yard line. Like it's going very, very close, and it's really exciting. The difference in the missions, of course, is the orbit. Parker is on the ecliptic, but also the instrument suite. So Parker has 4 instruments. 3 of them are in situ, and 1 is a heliospheric imager. So it's not taking images of the actual sun itself, whereas Solar Orbiter is. And so this, again, is a nice synergy. Next slide. So this is a movie of the launch. It's a pretty large movie. It may not work well with the streaming. But just so you can see, this is a Delta heavy. This is a major launch. This is a very, it's heavy because we had to get the spacecraft to Venus to use the gravity assist. If it doesn't play, that's okay. It's really just for like fun. And then here's an animation of the actual commissioning and the stages, the deployment of the booms. And then eventually the Venus flyby, which it did very quickly after launch, just 6 weeks, I think. And so this is Parker. It's also an amazing mission. I don't have time to talk about it, but I just wanted to show that because I didn't want to ignore it. It's such a major mission. Okay, next slide. Sorry about the animations not working so well. So one way that we can use these two missions in a way that will utilize both in a very synergistic way are where these different configurations are. So you can see sometimes Parker, which is the very close spacecraft to the sun, sometimes Parker will be aligned radially with Solar Orbiter. And in that case, because they both have in situ instruments and very similar sampling plasma properties, they're going to be looking or sampling the same solar wind plasma. And so the solar wind is constantly moving out from the sun. Can you go back one? Thank you. And so this is a way of multi-point measuring. And then in other configurations, IMF stands for interplanetary magnetic field. And so because the sun spins and there's a Parker spiral of the magnetic fields, sometimes Parker Solar Probe will be aligned on the same magnetic field line that's attached to the sun. And so that is a pretty strong synergy as well, being able to know that the particles that are coming from the sun at both spacecraft are connected to the same foot point. And then there are other configurations where Solar Orbiter will be looking at the sun and Parker will be close at like a 90-degree angle. And so because Solar Orbiter produces remote sensing, it will be imaging in providing the contextual images of the sun and what is happening between the sun and Parker. So especially if there's like an eruption, orbiter is going to be able to image that and measure some of the properties of that eruption because it can see it. And Parker will be measuring the plasma properties, the energetic particles. So when eruptions occur, things happen to the plasma. They get very energetic. You can have shocks, you can have many different things. So again, a very exciting combination, and there's been a lot of planning to plan these types of collaborative campaigns. It's hard enough with just the number of solar orbiter instruments for them to plan how they're going to collaborate there and combine their observations, but then you add Parker, and it took years of planning. So next, please. And you can just click 2 times because I think the list will fill out. So go ahead and click again. So this is just some of the milestones of the mission. Whoops, sorry, Dallas. There we go. So again, it launched in February of last year. The first Venus gravity assist maneuver was just this past December. And then August, just recently, there was the second Venus gravity assist maneuver. And again, November of this year is when the nominal mission phase, that's what MP stands for, and that's going to be the Earth gravity assist maneuver. So in March of next year, that's going to be the first close perihelion, which is about 0.32 AU. So keep your ears out for news of that. Solar Orbiter is probably not as well known as Parker, but these are pretty big milestones. Next, please. And this one is a video of the actual orbit of Solar Orbiter. So this is the 10-year journey, including the extended mission. The nominal mission is about 7 years, and many of these missions last well beyond that. So we expect that as well. And if you can see the animation working, you'll see the Earth and Venus, and Orbiter is the white streak. And you'll see flashes every once in a while, and that's the actual gravity assists. And you can see on the right, the key events that are happening. It's 2-dimensional image, but you can tell that it's getting kicked out of the ecliptic as it goes and uses these gravity assist maneuvers. And so by 2029, we expect to be over 33 degrees out of the ecliptic. This will allow us for the very first time to image the polar regions of the sun. Now, this may not sound that interesting, but it's actually very critical to modeling of the global magnetic field of the sun, which is important for space weather forecasting space and understanding space weather, understanding really what's happening on the sun. Not only that, but the solar activity cycles. So, being able to image the flows at the polar regions, the magnetic field structure on the surface, magnetograms. This is going to be neat. So that's, again, one of the unique features. And next slide, please. So the spacecraft itself, if you know about spacecrafts, it's a 3-axis stabilized spacecraft, sun pointing sun shield. Okay, so the shield itself protects the spacecraft and provides apertures for remote sensing instruments. You can click again, please. And this heat shield, because the orbiter is getting close to the sun, has to be pretty good at protecting the instrumentation behind it, right? So this particular heat shield is made of carbon fiber composite and then multiple layers of titanium. And in fact, it's the same material that the crushed burnt bone that these Stone Age artists used in caves. It's the same material. That material is blasted onto the titanium heat shield of Solar Orbiter. And it is excellent at absorbing heat and it won't decay. It's pretty neat. So this is a pretty wonderful engineering feat. Really. And just for scale, so this is the heat shield getting thermally tested in 2014. You can see the men and women, I think, also along the railing there. If you can click one more time. Just for more scale, I'm showing a photo just before it shipped off for launch, and you can see the 2 people standing there. I mentioned the heat shield of Orbiter, but Parker, again, is going closer to the sun, and it's not the same type of heat shield. Parker heat shield is made of 2 panels of carbon composite, and they're basically sandwiching a very lightweight 4.5-inch thick carbon foam core, and it has to be very light. It's a lot of energy to get these missions close to the sun, and so it has to be very light. And I think with Parker also, that was the heat shield was sprayed with some like white coating to reflect as much of the sun as possible. So the 2 different missions have different types of heat shields, but they're both incredibly effective. So next slide, please. So this is just a list of, I'm not going to go through these, but this is just to demonstrate how international this mission is. And so each of the instruments is led by a person, well, what we call a principal investigator, and those are the names you see there, and then their countries that they're from. And so this has been a really great collaboration between many countries, and it's complicated. The different space agencies do have different ways of reviewing, and so it was a very interesting way to do things, and not super easy. But again, you can see between the in situ instruments up top and the remote sensing, you were getting composition of plasma, energetic particle measurements, electrostatic waves, electromagnetic waves. So this is important for understanding the plasma, and then the remote sensing, again, is providing EUV, visible. I'll actually show you some data from this, so I don't need to go through all that. Next slide, please. And so you can see this is the where the in situ instruments are located. So there's a boom that you see sticking out of the spacecraft. That's where most of the in situ measurements or instruments are, and that's because they need to be away from the spacecraft. They might need to be electromagnetically clean. And so they're located along, and they're getting, again, magnetic fields, energetic particles, waves, different elements of the solar wind. And then if you click the next slide, these are the remote sensing instruments, which are almost all located on the right behind the heat shield. And so they're the ones that had those apertures, because they're basically cameras. And so those apertures that were through the heat shield, so these instruments are sitting behind, nicely protected. The temperature difference is crazy. They're actually kind of like near room temperature, and the heat shield is extremely high temperatures. The one that's different from the ones that are right behind the heat shield is Solo High, which is a heliospheric imager. And I'll show you some data from that. That's not looking directly at the sun. That's actually looking away from the sun, looking at the solar wind and the extended atmosphere. Next, please. Again, I mentioned the importance of the linkage, and again, I'm sort of beat this to death, but combining the in situ and remote sensing observations, these really complement each other, and they provide a holistic picture of the sun and the surrounding environment as well. And this is not data from Solar Orbiter, but this is just a demonstration of the coordinated remote in situ observations of, say, a flare source happening. You can see the UV and X-rays of the flare source in the lower left, and these are say it produces a jet that's seen in these two data. You can see the red outlines are the loops, and then the loop foot points are the blue outlines. I'm not sure you can see those circles in that UV X-ray image, but we can image that, and then as the escaping electrons from this flare, they may produce a radio burst. So if you see up sort of in the middle, the escaping electrons with the little arrows, those interact with local plasma. And so the frequency depends on the coronal height of the emitting particles. So we can tell something about the local plasma density with altitude. And then, you know, the spacecraft, if it's in line, and you can see the little image of the spacecraft there, you can track the electron burst where it passes by the spacecraft, and the arrival of the energetic electrons. They time the arrival of the escaping particles and the energetic ions. They provide a signature of fractionization, as you can see the energetic helium here. Again, so this is just a way of showing using the different types of observations to make the connection all the way from this flare that happened on the surface and how it's impacting the surrounding environment. Really important for space weather. Next, please. And so some of the sort of the top level science objectives involve looking at the sources of the solar wind, where does it originate? Active regions are one source, and so identifying the source directly by the wind, that by the time it gets to 1 AU, it's very, very challenging to identify where it came from, because there's a bunch of mixing that goes on in 93 million miles, and so you can't really tell a whole lot when it's by the time it's at the Earth. You have to get closer to understand the detailed physical processes. So can you run that little movie in the middle? One of the really cool things about Orbiter is when it is close to the sun, there are certain orbits where it will be evolving, or it will be orbiting at almost the same rate as the sun. And so it's what we call reduced relative rotation. So the relative rotation, you can see the little tiny dot is the spacecraft. I'm not sure you can see it, but it's able to hover above like an active region for almost a whole rotation in certain orbits. So this is actually, it gives a chance to study up close an active region for a long period of time. This is pretty incredible, actually. Next, click. We are going to be studying the solar transients, the coronal mass ejections that I talked about, and how that varies. These coronal mass ejections can produce shocks, and so we're going to be able to study those with Solar Orbiter, and also we do study these with other instruments as well. Next, click. There are solar energetic particles that get accelerated in different types of phenomena. So one of those is a solar flare. And so the first inset on top of this third thing here is showing like a flare can accelerate these energetic particles. And then the lower is this coronal mass ejection can also accelerate particles. It's very difficult to tell which mechanism, where it's happening. And so Solar Orbiter will be able to provide the relative importance of these acceleration mechanisms, again, because it's not at 1 AU where the particles are mixing. And so this is important for testing the relative importance of the two acceleration mechanisms. And next slide. Because we're going out of the ecliptic and able to look at the polar regions, we're going to be able to understand better how magnetic flux is transported and then reprocessed at high solar latitudes. So this is going to help with helioseismology, local helioseismology, basically to determine what is currently unknown properties of the solar interior right below the poles. If you don't know anything about helioseismology, it's a pretty neat field, but it requires these observations if we're going to have the local helioseismology at the poles. But also being able to probe these polar regions will allow us to probe even deeper into the solar interior because where you can use stereoscopic helioseismology in combination with near-Earth assets or observations such as GONG, SDO, these are other things. So anyway, it's again, multi-point observations will help. Next slide, please. And I'm just going to show, even though we're not in the nominal science phase, just some early science highlights. And I'll go fairly quickly through these just to provide sort of a flavor of what Solar Orbiter can do. There's the first orbit that it had, the energetic particle detector recorded several energetic particle events, and those are represented by those lines. And so this is even at a time when the sun is basically not very active, what we call solar minimum. And so this is pretty neat. And the other really cool thing that was a little bit of a surprise is that after launch, Solar Orbiter, we determined, was possibly going to fly through the comet Atlas's tail. And it did. The comet itself broke up right before we flew through it, but it continued to be bright. And so they did actually, what they think, get some measurements of ion scale waves, magnetohydrodynamic waves, and also maybe some cometary pickup ions. And so basically they're able to look at some of the physics due to the tail of the comet. And so that was kind of a nice little surprise. Next, please. This next one is just to show again the importance of the multi-point observations, which I've already talked about at length, so I won't spend a lot of time. Next slide. Yeah, some of these slides are really large, so I think they take a while to load. There we go. Thank you. And so we're looking at on the left, we're looking down from the North Pole, and so you can see the ecliptic, and you can see the rotation of the magnetic field as the sun rotates. And Solar Orbiter is near the Earth, if you can see that. Bepi Colombo is another mission that's near the Earth, and that's actually now near Mercury. And Stereo is another mission. So basically, by combining these different observations, they were able to model a coronal mass ejection. And so the observation in the middle is the observation made by Stereo. Combining these allowed the model on the right to be created. And again, this is not an easy thing to do. It requires a lot of different data. And so for space weather and models, this is great. This is great. Go ahead to hit the next one. I don't think I'm going to go spend time on this one after all. They did determine on the same event that it was a flex rope structure, meaning a helical structure. And so that is also important for understanding the impact potentially at the Earth. Next slide, please. The extreme ultraviolet imager on Solar Orbiter can take images in a variety of different wavelengths, and you'll see this here. One of the surprising discoveries that happened during the commissioning phase. So these instruments were just turning on just to test themselves. Like they weren't in their 10 window window of remote sensing science, whatever you call it. So what they discovered is on the far on the right, you can see what they are calling campfires. And so this is actually zoomed in quite a bit, and you can't see. I'll show, actually the next slide it will show you better. But there are these little very bright, like very, very, very compact, bright things happening. And so they're calling those campfires. They hadn't been seen before. These images that you're seeing here were the closest ever taken of the sun at this point. This is when Solar Orbiter was halfway between the Earth and the sun. So that's why we're able to discover new things, because you get closer, your resolution improves. Next slide, please. And so here you can see a better zoomed in little animation of the extreme ultraviolet. So this is in a quiet region of the sun. And on the left, you can see the movie. So the box is zoomed in even more on the left. And to demonstrate scale, you can see the Earth. So that little campfire, that little brightening in the center of that box, of the zoomed in box, it's kind of like the size of a country on the Earth, but that's very, very small on the sun. And so this is a neat thing to know, to understand. Maybe these have to do with why the corona is so hot, if these are happening all over. Next slide, please. I won't spend a lot of time on this, but this is another instrument that is also able to see these bright spots. And so this is the spectral imaging of the coronal environment SPICE instrument. The background is not SPICE, but if you click again, so you can see simultaneous extreme ultraviolet diagnostic lines. And so if you see the next there we go. If you see the series of images on the right, those are different lines. And the campfires that we saw on the previous, those are from a line that corresponds to about 0.6 to 1 million Kelvin. These other little ones that they're seeing in these data, these are actually, they span the range of temperatures from like 30,000 to 600,000 Kelvin. So they're a lot cooler. And so this is, again, understanding the difference between these very small scale phenomena is important. Next, please. And this is really just to demonstrate that even combining the two instruments, the extreme ultraviolet imager and the SPICE data, on one of these campfires, they were able to get Doppler shifts from SPICE. And so that gives us information about what's happening in these little compact areas. Next. And it's just exciting to show some of the early data. So I don't mean to fly past all this, but this was actually, this is an animation that was made prior to launch to show the different fields of view of a couple of instruments. So the field of view of the heliospheric imager is on the left, and then there's another coronagraph that shows the inner part. And you can see as solar orbiter goes from 0.5 AU and then back to 1 AU, it shows you the difference in the field of view, which is complicated when you're trying to plan for instrumentation, for data analysis, and for just, it's a very complicated thing when you're changing your location relative to the sun. Next, please. And this is just kind of a fun thing to close out with. So that's the heliophysics imager that is imaging the solar wind, but it also was able to catch these different planets. So you can see the very bright Venus. This is on its way to a Venus gravity assist. I think this was in December of last year. So this is why Venus is so bright. You can see the different distances. Venus is a lot closer to the spacecraft within 48 million kilometers. And if you click again, Earth and Mars, of course, they look also nice. And then all of a sudden they noticed, hey, wait, there's Uranus, like very, very small. Because it's about 3 billion kilometers away from the spacecraft. But if you click one more time, I think it'll zoom in a little bit. So there you see the sort of the little bright spot. But that was kind of, again, really cool to discover. And then there was also a close-up of the moon and the Earth. I think if you click one more time, or it's just slow. There we go. Even though this is difficult to see, you might be able to tell that in the top right corner, it's a little brighter, and so that's actually the moon. So again, pretty cool. Not necessarily what we were expecting. And next, this is just to show the line of sight for those previous images of the planets. So you can see solar orbiter. Venus is the closest one. That's why it was so bright. You can see the location of Earth and its orbit in Mars, and you can see that's why it looked. And then if we're looking from the spacecraft, our field of view on the right, you can see again what it looks like from the spacecraft and why those planets aligned like they did. That is all I have. So next slide is just a big thank you. The field of solar physics has been really advancing, and partly because of all these wonderful new data that we're collecting, but also there's been a large increase in sophistication of modeling. And modeling is really important to combine with observations, even though I focused on observations during this talk. And so for folks that may be interested in this field, I'm very, very optimistic that it will be a pretty healthy field. It hasn't always been. It hasn't always gotten a lot of attention. Now that space weather, which of course the sun is a major part of and drives it, space weather is gaining a lot of attention both nationally and internationally, and for good reason. Our satellites are at risk, our astronauts, and our technology. And so as that becomes more and more known, solar physics is going to become more and more relevant and important. So I highly encourage anybody that's looking to find a fun field to join us in the field of solar physics or heliophysics. And with that, I will end. Thank you.
All right, and thank you, Holly, for an outstanding talk. It is kind of nice to see the sort of evolution of the field of solar physics as we go, both from the ground-based to the space-based observations. And One question that I have, while I remind our listening audience, if they have questions for our guest, please feel free to put them in the chat of the live stream, and I will be glad to share them as we go. But one question I have, thinking personally of my students that have been interested in doing space physics or astronomy related stuff, what types of sort of academic preparedness would you lean them towards if they were students that were looking to get into the field of solar physics?
Great question. Plasma physics, plasma physics, plasma physics. I think that is really important if you're going to go into the field. Astronomy doesn't necessarily, or astrophysics, the stuff that's well beyond, it's not as crucial to understand the actual physics of the particles and the interaction of the radiation, and so that's highly important. But also, electromagnetism is a crucial, fundamental part of it as well. And so E&M, plasma physics, really, I think, is all the fundamental physics. And that sounds, it's not a very great answer, but I think especially E&M is important. And also, if there are chances for internships, I mean, that's how I got into the field. I had an internship where I was able to see the data of the sun, and back then it was not nearly as cool as it is now. But yeah, if you have a chance to intern somewhere, that's a great way of also just trying to test out different things and see what you may love. But plasma physics would be my top priority.
Okay. I actually have a question from one of the students. Ellie Jones asked, will we be able to use the data from Parker and from Solar Orbiter to help generate more 3D maps of the corona and the plasma as much, or will we need more, or will we need additional instrumentation to be able to pull that off?
That is a fantastic question. And it's always interesting because when we have instrumentation that can be taken from the ground, certain lines, certain wavelengths we can observe from the ground. Certain other wavelengths, like extreme ultraviolet X-rays, we have to observe from space. And so the instrumentation that's actually going to help with the three-dimensional map of the coronal magnetic fields will be instruments that we actually have that we're building now that will be on the ground. And it's not that we shouldn't put them in space. It's just very hard to convince agencies to spend money to put instrumentation in space that can be obtained on the ground. So for the particular issue of obtaining those three-dimensional maps of the coronal magnetic field, in fact, it's the instrumentation that we are collecting on the ground, or that we will be, and that's really part of what COSMO is. And it also helps to have a network of observatories on the ground so that we're covering a lot of different longitudes. And that is also something that we are hoping to do in the future. Now, space-based observations help with many other things that we can't do from the ground, including seeing the corona in all of those different wavelengths in the extreme ultraviolet. So in a lot of ways, the space-based observations from SDO, which has been up for a long time, Solar Orbiter with the remote sensing, those will help us understand some of the dynamics and what's happening with those magnetic fields and solar eruptions. But it doesn't allow us, getting the actual magnetic field of the corona is so difficult. And so, again, it requires the spectroperimetry that I talked about earlier.
That is great to know. I had one other question that came up from my perspective, just looking at the stuff that you laid out with Cosmo and sort of the ground-based instrumentation piece. And I know you've talked about the observers that they have for HAO, but how would students or solar scientists, yes, I am sort of asking this as a personal question because I'm always interested in trying to get back into the field sometimes, but how would people that are interested in the field, or people with experience, and even those that are coming in through the academic pipelines that may not have the experience, how would we get involved in a project like that?
Yeah, so there are a few things at HAO. We have internships and programs. And we will bring sometimes students in, especially during COVID, it's been a little different, but normally if you're interested in like building instrumentation, we've mentored students to bring them into the lab and actually help with building the instrumentation. For folks that are interested in space weather forecasting and to actually see how that's done. For instance, the NASA Goddard Community Coordinated Modeling Center, they have a space weather boot camp. And so you can go and learn about the relevant science that is needed to really understand forecasting for space weather and these solar eruptive events and the energetic particles. And so that's more of an operational way of looking at it. And that doesn't mean, it's actually good to have both types of experience, meaning the operational and then the fundamental research. But, you know, there are programs in many institutions, and since I'm speaking from my own experience, where if you wanted to, for instance, like I said, be in the lab and see how things work, there are programs now for people that are already experienced. Just reach out to colleagues. I mean, Erin, you should come spend time at HAO once we're back in the office. But yeah, reaching out to colleagues and saying, hey, can I come visit for a week and, you know, sit in your meetings, or being scientific meetings, not my boring administrative meetings, but, you know, really reaching out to colleagues, going to the scientific conferences, like the AGU. You remember Shine is a really good workshop to get people together and really talking and interacting. So yeah, I think there are many different routes that can be taken, but it involves either networking or kind of knowing who to talk to. So I'm a good point of contact for that kind of thing. I have, you know, some contacts at NASA, of course, but other places. So I'm not sure if that really answers your question, but it's exciting at the prospect that people might be excited enough to reach out.
It does give some openings, because I do have some students that have expressed interest in being involved in things, and I know I sat in sometime over the summer. I sat in on part of that punch working group that Craig DeForest and Nikki Vile were working on. So, and I know I've got some students that were interested in that too. Craig came and gave us a talk last year, and I was curious. One of the things that I was curious about was how will the observations from some solar orbiter and Parker and the ground-based observations also potentially tie in or feed into the punch mission and all the other solar missions that are going on.
Yeah, it's fun because there are so many ones that are even coming online, you know, in a few years. Punch is one of those really exciting missions, and that's of course looking more out at the solar wind in the heliosphere. And so, just as an example, because both Parker and Solar Orbiter have heliospheric imagers themselves, they're not exactly the same as what Punch is going to be creating, but they can also provide sort of multi-point observations as well, depending on where they are. You could combine all of that information, which would be pretty neat. And so we're excited about Punch in that respect. But also, it's kind of like you have the missions that provide some of the context of the environment beyond the sun, in between the sun and the earth, and Punch is one of those. So understanding the solar wind is a major part of I still consider it solar physics, even though some people would call it heliospheric physics. But also, you know, combining that with what's happening on the sun. And so it's in a similar way of Solar Orbiter using its remote sensing and its image and its in situ, Punch will just be another wonderful addition to the actual solar wind studies and research that will happen. In terms of ground-based, I'm not sure there's a ton, as much synergy between Punch and the ground-based observations, because the ground-based observations really are focusing at the sun and just close to the sun in the inner corona.
Right. Well, I'm going to give our audience one more chance to ask questions and see if anybody has anything. But it has been great to hear all this information, and great to hear about a all the current developments in solar physics and in the larger heliospheric context, but it's always nice to focus on the sun occasionally.
Yeah.
Actually, had a question from a viewer, Brandon, asking about space weather, and does space weather actually have impact on Earth weather, and does it affect
Oh,
some of our Earth weather situations?
That's a really great question. Now, space weather itself, it's a little bit of a, I mean, it's called space weather. It's very, very different than the weather on Earth, but there's not an impact from space weather on Earth's weather or climate. So space weather really impacts phenomena like the aurora that you see. It impacts, it creates currents that can cause power outages. So space weather is really impactful in terms of technology, satellites, astronauts who are more susceptible because they're above the magnetic field of the Earth. So the magnetic field of the Earth and the atmosphere of the Earth protect us from those space weather events. So it's really our technology that's the susceptible part. Now, I don't even know why I'm opening up this can of worms. Now, of course, there is a small correlation, not big enough to explain climate change right now, but the sun's activity levels, and so it goes through these cycles of solar minimum and solar maximum, those can impact the overall global temperature, but again, not enough. It's a small impact relative to the changes that we're seeing now. So that's why I didn't want to necessarily bring it up in that context, but there is an impact from the activity on the sun, but that's because of the radiation that's coming from the sun and the sunspots. It's not because of these coronal mass ejections that are hitting the Earth, if that makes sense.
That does help out, and I was glad to hear that question, because I was curious. I know we brought up space weather, and for those of us like myself and like you that are in the field, space weather is a common term for us, but sometimes in the context of the community, it's a little harder to quantify what exactly is space weather relative to the terms that we normally run into.
Absolutely. Yeah, it's very, very different, even though we even sometimes in the media will call these CMEs or these solar storms solar hurricanes. And that's just, they're really very different phenomena. Even the solar wind is nothing like wind here on Earth. It's very, very, very diffuse particles that are blowing away, but it's not like wind. So sometimes it's very confusing, I think, for the public.
Yep. Well, I appreciate everyone for tuning in and seeing no further questions. Thank you again, Holly, for an outstanding talk, and I will encourage those of you that have tuned in today. Please feel free to join us next month for our next installment of the Physics and Astronomy lecture series. We'll be talking to Professor Raymond Fry of the University of Oregon about gravitational wave observations with LIGO, and hopefully we'll get to have more information on that going forward. Expect more announcements as we get closer to that date. But thank you everyone for coming, and hope you enjoy the rest of your day.
It's wonderful to see you, Aaron. Thanks again.
Likewise.